Yeah. So what I'm not going to do is I'm not going to explain in more detail the technical theory of sheaves and trace functions than Philippe. What I'm going to try and do is give you some intuition for how to think about sheaves. So the moral of the story I'm going to tell you is that the way you should think about a sheaf, at least some of the time, is as being similar to the system of solutions of a differential equation. And the way you get the differential equation, if your sheaf corresponds to an exponential sum, you look at the corresponding exponential integral. And the answer is you use the correspondence between exponential sums and exponential integrals. So, for instance, the most popular sum we've been talking about is, of course, the Klostermann sum, which looks like this. Sum x and fq. The additive character of x plus ax inverse over q. And we can compare this sum to an integral, the Bessel function, which I'm going to write in a slightly different way, but to make it look more like the Klostermann sum. The integral from 0 to infinity, x of x plus a x inverse dx over x. And I think in the standard notation, this is like j0 of square root of a or something. So just in terms of how they're defined, these functions are very similar. And they also often show up together in the same context. We saw in Philippe's talk when you're studying the divisor function, both these will often appear. And we saw in Ian's talk when you're studying the representation numbers of quadratic forms, both of these functions will appear. But despite the fact their definitions are similar, you won't directly see any connection between the values of this function, just because integration is so different an operation from finite summation. This is a very smooth function. This function is not remotely smooth. There should be no x here. There's no correlation between the function evaluated at a and the function evaluated at a plus 1. But there are connections between concrete properties of these two functions if you know where to look. And the constructions are mediated by the associated sheaf. So we have the Klostermann sheaf here. And we have a differential equation here, which is, I think, is something like a d squared f dA squared plus df dA equal to 2 pi I f. So this is a kind of general principle that all these kinds of exponential integrals will satisfy differential equations, which I think you can prove by an integration by parts argument. I mean, I may not have gotten constants exactly correct, but it's something like this. And I'll explain 3 different kinds of connections between the Klostermann sum and Bessel integral that are relevant to some extent to the analytic theory of trace functions.
Is that an a in front of the second derivative? A second derivative?
Yeah, that's an a, yes. Yeah, and that gives a differential equation a singularity at 0, which is important because this sheaf has a singularity at 0. So the first connection I'll talk about is involving ranks and sharp constants. The second connection I'll talk about is involving monodromy and equidistribution. And the third is involving asymptotics and local monodromy. And if there's time, there will be an appearance here of a local Fourier transform. So the so 1 ranks sharp constants. Example 1.1. So the Weil-bound for the Klostermann sum, which is by far the most important result about these sums in analytic number theory, is 2 root q, maybe. I think the less than is actually, yeah. So this is the most important thing you use when you're studying these guys. The constant here is not tremendously important in analytic number theory, but it's very nice and explicit, and it's sharp. This can't be improved. And this number 2, it comes from, it's the rank of the Klosterman sheaf. Two is equal to the rank of Klosterman sheaf. And it's also equal to the order of the differential equation. Which means it's also equal to the dimension of the space of solutions, of local solutions. Space of solutions. So this is a general principle. So the sharp constants we're working with, the sharp constants on our Weil-bounds, will always equal the order of some corresponding differential equation. Maybe not always, but will usually equal the order of some corresponding differential equation. And this is going to be mediated by the sheaves. So the principle is that the sharp constant in Weil-bound, it equals the rank of the sheaf, is equal to the order of the differential equation. Actually write it differently. Not write that here. Equal to dimension of the space of solutions is equal to the order of the differential equation. So these two things are both concrete objects, fairly, but this order of the differential equation is not, it's not ideal for what I want to do, because I really want to connect it directly to this properties of this function, this integral, that are more analytic. And like the order of the differential equation is kind of something you compute just by doing some algebraic manipulation of these terms, doing integration by parts. But there is a way to compute this, which is to use stationary phase. So this can often be computed by stationary phase. So the idea is we're going to let some parameter go to infinity and try and study the asymptotics of our function. And it'll split into a sum of different terms. And what we'll often find is that in good situations, the other solutions of the differential equation will be the same terms with different coefficients. So the dimension of the space of solutions will just equal the number of terms. So for instance, for this integral, if we let a go to infinity, integral from 0 to a to infinity, e of x plus a x inverse dx over x is equal to the integral from 0 to infinity, e of root a times x plus x inverse dx over x. And so as a is going to infinity, this function is going to get more and more oscillatory, and it's going to cancel more and more, except near the critical points. So this is the principle of stationary phase. It lets us write an asymptotic for this. The critical points are going to be the solutions of d dx x plus x inverse equals 0, which is 1 minus 1 over x squared equals 0. So they're going to be x is equal to plus or minus 1. So we're going to have a contribution from 1, which is e of 2 root a over root A. So here it looks like I'm being punished for my change of variables of the Bessel function, but I think I'll be rewarded later, so it's OK. Minus 2 root A. OK, so there's two terms, and it's a rank 2 equation. And this is actually a pretty general phenomenon. I'll give some other examples. Well, by the way, I'm going to be vague about a lot of these connections, a lot of the things I'm doing to try and give an intuitive overview. So definitely, if you want anything more specific, you want details, please ask me questions. Okay, so example 2. If you look at this integral, e of f of x, t f of x dx, and like this exponential sum, t f f q. If f is a polynomial of degree d, d non-zero, we have the following Weber-bound. And the constant is exactly d minus 1. It's a fun fact you can prove by elementary methods that if any bound holds for this function, the constant has to be exactly d minus 1. What? T times f of x. I don't really need a t here. Let me do it without a t. F of x over q. Yeah. We should expect to see the analogous constant appear on the other side. And when we do, this is going to be dominated as t goes to infinity by the critical points of f. And how many of those are there? There's d minus 1. There's d minus 1, which is the roots. And I'll give one more example of this phenomenon, which is the hyper-Klostermann sums. So for the sum over x1 through xk minus 1 in fq of the exponential of x1 plus xk minus 1 plus 1 over x1 times minus 1. Okay. This is another way of writing down the Klostermann sum. This sharp bound is k times q to the k minus 1 over 2. And then this, or we should put an a in here. Yeah, k of a. This function, x1 plus xk minus 1 plus 1 over x1 through xk minus 1. I'm not going to calculate the derivative, but you can easily do it. And this has k critical points. It's basically when the xi are all one of the k-throughs of unity. Yeah. Well, yeah, exactly. This is for polynomials. Yeah. Yeah. Okay. So the formula, there is a formula for rational functions, but it's something like you take the sum of all the orders of the poles, and then you also add up the number of poles, and then you subtract 2. There's some explicit formula, but I mean, it's just whatever the formula is for the number of critical points for a generic function with that many poles, I believe. Yeah, no, this is only for yeah, this is polynomial, which maybe was not clear from my handwriting. So these examples show, I think, already that there's some kind of connection between these two objects. But let me make it a little bit more clear what's going on, maybe. So I'll go to section 2, monodromy and equidistribution. So I mentioned earlier this constant is sharp. And in fact, let me reiterate, all these constants I've written down are completely sharp. You cannot improve this by any kind of constant factor. Now, this should be a little funny. So normally, in analysis, the way it proves something is sharp is I'd restrict to some special case where I can calculate it explicitly, and I check it's sharp on that special case. But like the Klostermann sum is not any easier to compute for any value of a than any other, except for 0 where the bound is not sharp. So one can't show the bound is sharp this way. The way we show the bound is sharp is by using equidistribution theory. What we're going to do is we're going to treat the Klostermann sum as a random variable. We're going to normalize it, like KL2 of a q over root q as a random variable. So view random variable with a uniformly random. And f q. And we're going to study the distribution, and we're going to take the limit as q goes to infinity so that we have a hope of the distribution converging. Yeah? No, sorry.
So then I can ask even 0, if you prompt me for a question, a and f q is the value 0?
It doesn't really matter because I'm going to take the limit as q goes to infinity, so it's not going to affect the distribution. Yeah. You can do whichever one you like. As q goes to infinity, the distribution converges. I'm just going to draw it to this one. The semicircular distribution between -2 and 2. So this is supposed to be a perfect semicircle. So this distribution, it shows up a lot in mathematics, including, it's the same with the Tate law for elliptic curves. It also shows up in random matrix theory. So it's fair to say that when we see this distribution showing up, we don't know exactly what's going on, like what causes it. So what we have to do is maybe look for more examples it becomes clear. And so if we do the same thing, same for the hyper-Klostermann sums, and we normalize them by q to the k minus 1 over 2, the limit is, if k is even, the distribution is you take a random element of a certain compact group of trace of a Haar random element element of USP. Okay. And for an odd, we take a same thing, but with a different group. So in U, SU. Okay. So the distribution we're getting, it always is going to arise from a compact group as the trace of a random element, and random according to the Haar measure. So these distributions tell us, they've got to be controlled by some hidden group structure. And it really is hidden. There's no way that looking at this sum for like a million years and doing analysis, you would never recover, I don't think, the group SP2K or SLK. You have to go to the algebraic geometry where that group is the monodromy group. So
What's that second group that you wrote?
This is SUK. Yeah.
And the first group was what?
USP. Yeah. Sorry, I went a little over there. So the real theorem, which is this one, is that for a general trace function, which comes from a representation of a representation rho from the Galois group of FQ join T to GLN. The distribution is controlled by, you take the image of rho restricted to the geometric Galois group. And we take the Zariski closure. Which is called the monodromy group. So I think people were asking in some of the previous talks, what do these representations look like? Like, how can you describe the representation associated to Klostermann sums? And it is legitimately quite hard, but one thing we can describe is we can figure out what the image of the representation is. And this is exactly this one of these groups. Well, it will be the algebraic group version, but it's one of these groups that you can see very clearly if you plug it into a computer and just tell it to calculate a histogram of this distribution. Well, maybe it's not always so clear because sometimes two groups can have the same distribution. Sometimes two groups can have very close distributions. But in general, it works pretty well. And so what I'd now like to do is explain what this looks like on the differential equation side. Just let me write down here. Another kind of principle. If the, that way. The monodromy group of the sheaf, which controls equidistribution, is equal to the monodromy of the differential equation, which I'll explain what that is, of the diff EQ. As long as the differential equation has regular singularities. Which just means the solution f of z near a singularity looks like z to the s and not, yeah, f of z looks like z to the s and does not look like some crazy exponential function. Or wait, yeah. All right, so let me go over here and explain what I mean by monodromy of differential equations. So this is a very classical topic. Given an ODE on C with singularities A1 through AN. If we have a point in C not including these singularities, we can look at the local, all of the system of local solutions at the point x, V the vector space of solutions at x. And then given, if we have any path in C minus these solutions that starting in x and returning back to x, we can analytically continue these solutions along the path. And we get more solutions which might be the same or they might be different. So given a path from x to x in C minus A1 through AN, we can analytically continue along the path to get a map V to V. And what this will give us is a representation rho from the fundamental group of the complement to GLV. And this phenomenon where we get different solutions than what we started with is called monodromy and the image of rho. You can maybe take a topological closure or a Zariski closure or something is a monodromy group. So my claim is that this group of the associated differential equation will control concrete properties of sheaf like equidistribution. So let's see some examples. Yeah?
So you said take a Zariski closure, but it looks like the image would be discrete. Is that right?
Yeah.
So why would you take a Zariski closure?
Or wait, so the image is not, well, for two reasons. So first, it's the image of a discrete group, but there's no reason to believe that it's discrete. If the monodromy around this loop is some like weird transcendental, and the monodromy around that loop is some other weird transcendental, like we could have some crazy loop that would be arbitrarily close to identity. And the second thing is, the reason I want to take the Zariski closure is I would really like to obtain an algebraic group, rather than an arbitrary Lie group. And I would like to compare it, and I want to compare it to these groups, which are always like the maximal compact subgroups of algebraic groups. But in the example that I talk about, the closure won't matter too much. So let's start with the simplest possible example, which is our exponential sum is not going to be sum, it's just going to be a multiplicative character. And this will be of order D. And so the associated sheaf will have a character sheaf. The character sheaf. And our associated integral will not be an integral. It'll just be f of z equals z to the c. It's going to be a power of the parameter. I mean, it's a multiplicative character, right? And the way, the rule that relates which character you take to which power is the denominator. This should be a rational power, and the denominator should be the order of the character. So you have a little bit of freedom. It's not like a one-to-one correspondence here. And of course, there's a differential equation. The differential equation is df dz equals c over d f over c. Okay, and this differential equation has monodromy. We got a singularity at 0 and a singularity at infinity. And if you let z go in a loop around here, this multiplies f by e of c over d, which is a d root of unity, a primitive d root of unity. So the monodromy representation is going to be a representation from the integers to GL1c, which just sends n to e of n c over d. And then the monodromy group is the group of d roots of unity. So if you trust me, you should expect that this character to be equidistributed in the d roots of unity. And of course, your trust would be validated because this character is valued in the d roots of unity, and it does take each value equally often. So this is equidistributed. Yep. Yeah, E of C over D.
But you have other loops that don't go around 0, for example, they're retractable, and then
Well, that'll return you to your original value.
right. So your representation is doing what to it? It's just leaving it alone.
Yeah. So right. So I went quickly over this. So I probably should explain. So this fundamental group, it's like the group of loops up to homotopy because of the way analytic continuation works. If you slide your loop over, you're not going to change the finishing value. And so for the complex numbers minus 0, the group of loops up to homotopy is just the integers. It's generated by this one loop. And so we only have to calculate what it does on this one loop. And so the point of the analogy I'm making is not just that we can compute the equidistribution, which is kind of cute. I want to make it more intuitive, the way in which like the Galois group that's appearing over there is really an analog of the fundamental group that's appearing over here. And that if we have some classical understanding of monodromy, we might be able to apply it in this world and get something. So let's talk about a different sum, which is like x in fq not 0 or 1. X. So let's throw in the minimum number of multiplicative characters to make the sum not trivial to evaluate, which is 3. We can do this. This is a function of t. And it's analogous to a classical sum. I actually need to look this up. It's analogous to a classical sum in a classical integral, the hypergeometric function. All right, let me just make this up. Of a, b, c, z, something like the integral from 0 to 1, z to the a, 1 minus z to the b, 1 minus, or this function of t, 1 minus tz to the c. Yeah, these parameters are not quite right, but it's just like some kind of linear combination of these. And there's a constant proportionality here also. So because these, yeah, it was z. Yeah. Probably should be an x instead of a z because it's a real number. So because these multiplicative characters I told you are analogous to powers, this exponential sum is analogous to this exponential integral. So this is a hypergeometric function, and this is it satisfies a hypergeometric differential equation, and this is the trace function of a hypergeometric sheaf is what the creative name that Katz came up with.
So is there also a singularity of like x is t inverse, or does that away for some reason?
Oh yeah, sure. Good point. I need to also not sum over t inverse. Yeah. Although probably a better idea would be to just take the convention that whenever you plug in 0, the character is 0. So this hypergeometric function has singularities at 0 and 1. So this is here the monodromy can get much more interesting because the finite group of this space is much larger. And the monodromy is a classically studied topic. And let me just say, well, the monodromy is usually large, but occasionally finite. And when it's finite, that has a kind of interesting consequence, which is this integral has like an algebraic solution. Its solution can be expressed by taking like roots or some polynomial equation. And what you can do is you can basically discover the same theory applying to the hypergeometric function. So this will usually, the hypergeometric sum, this will usually be equidistributed in a large group, but sometimes infinite. In a large group for chi1, chi2, chi3 special, it's finite. So this function, for some values of chi1, chi2, chi3, this sum might take only finitely many distinct values. So I really mean the singularities of the differential equation. So you can write down a simple differential equation for this. It's especially easy to write down using hypergeometric power series. And if you do, you'll find that one can analytically continue a solution everywhere in the complex plane except for these 2 points. That make sense? And I have one more example. So I tried not to make a very big deal earlier about this requirement of regular singularities, but it is a problem that does crop up. And so let me give an example of what goes wrong. We're going to consider another case, or 2.3, another simplest function. It's now going to be just an additive character. So E of A over Q will be our exponential sum. Okay, and we of course have the associated integral E of Z, which satisfies a perfectly nice differential equation, but it does not have any singularities in the complex plane, and it does not have any monodromy, right? This is a single valued function. No matter what path you take, you'll always return to the same value. So this has trivial monodromy. But this function does not have trivial equidistribution. I mean, it's quite evenly distributed on the unit circle as you let A vary. Has a non-trivial distribution. And if you look at the associated sheaf, the Artin-Schreier sheaf LP, from the way it's constructed, you can check that it has a monodromy group, monodromy mu q. So what's the problem? The problem is, of course, that this function does not have a regular singularity at infinity. And so let me have like an aside, or let me not write it here. So when the differential equation has irregular singularities, get some more chalk. Do we just we use the differential Galois group instead. And the differential Galois group is going to be some group of automorphisms of the space of solutions, which preserve all algebraic relations between the solutions and their derivatives. Automorphism. So it's a generalization of classical Galois theory from polynomial equations to differential equation. But I'm not going to talk about it very much because it's kind of abstract and algebraic, and I'm trying to make things as concrete and analytic as possible. But what I will say is it's sort of clear the monodromy group is always contained in the differential Galois group, because whatever relations I write down among the solutions, if they're satisfied at the start of my path, they'll certainly be satisfied all along the way, and also at the end of my path. So you sometimes need a slightly larger group. And one thing I have conspicuously failed to mention in my examples is the Klostermann sums.